Hello everyone. Thanks for taking the time to watch my video. I guess this is a pretty important day for me as I will be posting my first ever YouTube video. So without any further ado, let's kick this off. I chose the Nomad 2018 Predicting Transparent Semiconductors Kaggle Challenge, that's a mouthful, for my first project in this advanced modeling course. This challenge struck me as interesting because I had a chemical engineering lab in undergrad where we tested the energy retention properties of some compounds like those I looked at in this challenge. The challenge focuses on structures that are called transparent conductors. Now, transparent conductors are important compounds that conduct electricity and don't absorb much visible light. And they're used in quite a bit of common technologies such as photovoltaic cells, television screens, and touch screens. Now, the two important properties of transparent semiconductors are formation energy and band gap energy. Now, there are methods for determining these properties. However, they are based on something called density functional theory, and I guess calculations based on density functional theory take supercomputers thousands of hours to run, which gets expensive. So the Nomad team challenged data scientists to come up with cheaper ways to predict these properties. This is an ongoing competition that ends in the next few days. All right, let's jump into the math. I know that's what everyone is excited to hear about. So as always, let's kick this off with exploratory data analysis. First, let's take a look at the variables we were given for our analysis. I mentioned before that we would be trying to predict formation energy and band gap energy for transparent semiconductors. To make these predictions, we were given a few variables. First, we were given space group. Space group is basically a label that indicates what types of symmetry are present in a particular structure. That's actually about the best I can explain it. I started digging into space groups a bit more, and apparently symmetry can be present in 4, 5, and even 6 dimensions. That kind of physics really starts pushing the boundary of my brain because I don't understand how a crystal can display symmetry in 6 dimensions. Now, while space groups are a bit complex for me, I was able to understand the second variable pretty easily. The number of atoms is simply the total number of aluminum, gallium, and indium atoms in the structure. We were also given the percentage of total atoms that were aluminum, gallium, or indium. That's pretty straightforward. Lastly, we were given 3 lattice vector lengths and 3 lattice vector angles. Lattice geometry is another concept that I'm struggling to wrap my head around. Put simply, though, the lattice vectors and angles are used to describe the overall shape of a crystal structure. So those were the variables we were given. I eventually tried creating some of my own variables. The two I had some success with were modified versions of molar weight and heat capacity. I say modified because I didn't take into account oxide groups attached to the metals, but that shouldn't matter here because the ratio of metals to oxides are the same for each component in this data set. Let's kick off our exploration with some bar charts and histograms. On the top row here, you can see space group and number of atoms. Note there are only 6 unique space groups and 6 unique atom counts. That will come into play later on. On the bottom row, you can see the compositions. All 3 elements are absent from a sizable percentage of the structures in the dataset, which is why you see the large bars at 0. Other than that, they are mostly normal. However, there are slight skews to the gallium and indium concentrations. Alright, more histograms. These are the lattice geometry variables. You can see that these parameters tend to be distributed in several clusters. I'm not sure exactly why there are these clusters. Again, the physics behind some of this stuff is pretty rough. 2 more histograms, then we can move on. These are the target variables, formation energy and band gap energy. They are both skewed distributions. The formation energy distribution looks like it could be bimodal. Before moving on, though, I should probably mention here how great this data set was to work with starting off. It was pretty much already cleaned because the input variables were theoretical in nature. So there was not any missing data. I'm not sure if there were really even outliers. You could point to those high points on the formation energy distribution and call them outliers, but I wanted to leave them in the data set because I don't think they were high because of measurement error, and I'm not sure this data set is a random sample of possible structures. Now it's time to look at what correlated with the target variables. By far, the variables that showed the most clear correlations were the lattice vector lengths. You can see from these charts that there are very, very clear relationships between the vector lengths and bandgap energy. You can see, though, that there are different linear relationships for different groups of data. So I was thinking about how to break these up. Would I come up with a crude tree-based sorting algorithm? Could I use a clustering technique? Well, it was even easier than that. Recall that there were only 6 unique space groups and 6 unique atom counts. Well, it turns out that there were only 10 unique combinations of space group and number of atoms. So I created another variable that labeled each record based on its space group atom count combination and came up with this. Now, look what happens when we plot lattice vector length against bandgap energy. It's pretty clear how I can break these up. So this formed the basis for most of my models to predict bandgap energy. So while I thought predicting bandgap energy would be pretty straightforward, many of the input variables did not have clear correlations with formation energy. However, bandgap energy did. So my strategy here was to predict bandgap energy and then use that prediction as an input variable for my formation energy model. Okay, time to jump into the predictive modeling specifics. For this presentation, let's look at the results of 5 of the models that I built to predict bandgap energy. The mean squared errors and standard errors come from model validation. Before I started building models, I split off 30% of the training data as a validation set. I should probably also mention that I standardized the numerical data. Okay, my first predictions just used every input variable in a multiple linear regression model. As you'd expect, this model didn't perform that well. The mean squared error was greater than 0.1, which was significantly higher than the other models that I tried. Obviously, this was never going to work well, but I wanted to come up with a baseline. The next 2 models were actually sets of 10 models. What I did was create a separate model for each unique combination of space group and atom count. For the simple linear model, all I did was fit a quadratic equation to a lattice vector length and either molar weight or heat capacity. I selected the variables that gave the lowest validation errors. For the lasso model, I included all of the input variables and quadratic terms for each lattice vector length. I used the generalized linear models package in R to determine the minimum lambda. Then I used that minimum lambda value when making predictions on the validation data. Both of these models worked pretty well, though on average the simple linear models outperformed the lasso models. I was able to get a little bit better validation results by combining the results of these 2 models into a hybrid. Basically, for each space group atom count combination, I selected either the simple linear model or the lasso model. This improved validation errors slightly. Now, the last type of model that I worked with was extreme gradient boosting using the XGBoost package in R. This model was the winner based on validation errors, and I really learned a sobering lesson here. I probably spent 95% of my time on EDA and trying to fine-tune my linear models using the space group atom count combination and polynomial fits, Basically, I spent the first 4 weeks on that, and within about 15 minutes of playing with XGBoost, I had already improved my predictions. So yeah, next time I need to spend more time on the so-called cool stuff. So this is what makes XGBoost smarter than I. When I was looking at the data, I didn't think that lattice angles would be all that useful. I couldn't make any sense of a relationship between them and band gap energy. Turns out XGBoost thinks they are important though, along with the lattice vector lengths. Space group and atom count, not so much. Okay, so that's how I predicted band gap energy. Now on to predicting formation energy. I really focused on two techniques here, the lasso and XGBoost. Once again, XGBoost wins. It had lower prediction errors or validation errors than the lasso method. Once again, let's take a look at the variable importance plot for the XGBoost model. This is more or less in line with what I would have expected based on my own exploratory data analysis. There is one exception, though. Recall I felt that band gap energy would be a good predictor of formation energy. Well, not in this model. That's pretty much the only variable that didn't make it to the party here. Let's take a look at how I did on the leaderboard. I'm in the middle of the pack, on the back end of the middle, but in the middle nonetheless. Right now, I sit about 600th out of around 860 teams. This isn't great, but for my first Kegel competition, I'm not too unhappy with the results. Most importantly, I think I learned something from this exercise, and it's that I need to devote more time to machine learning techniques like extreme gradient boosting and neural nets. Well, that wraps it up for my presentation. Thanks for taking the time to watch this, and I'm looking forward to watching some of your presentations in return. Take care.